All right, stat students. So we have two more topics that we need to talk about. We have approximate positions of center and then resistance statistics. Okay, so that's going to be our lesson today. Hopefully this doesn't take too long. I don't think it will. But let's go ahead and write in our notes, make a new section, draw a line. We're going to say choosing approximate positions of center. So we've talked about in a distribution, like when we see the graph, that the center is that balancing point for the distribution. Hold on, it's awkward to have my camera over here. Let me move that right there. Okay, there we go. Now we're ready. We talk about the distributions. It's going to be that balancing point. So we're going to draw three distributions. One of them is going to look like, actually, I'm going to go ahead and make sure I limit myself here. So we're going to make 1, 2, that flatter. And I need you to draw this in your notes, please. There we go. We're going to make 3 distributions. So the first one, which I utterly did a terrible job. It's kind of hard to draw these with. That's fine. Okay. The first one's going to be symmetric, so you can draw yours better than me if you like. The next one is going to be skewed right. And then the last one here is going to be skewed left. So we need to put little tick marks where we think the mean and the median are going to be. So will that be here? Will that be here? Where will the mean and the median be approximately based on just the shape of the distribution? That's what we want to know. So yesterday we had drawn that graph talking about the distribution for income, household income, and that was pretty severely skewed to the right. And we said we used median to help explain that. So in your notes you have that graph. I think it's what you have last drawn, and we said the median was going to be at the 50% mark. It's sort of the halfway point. So that's sort of comes to mind on this, and that's typically going to be the whole idea. So the median, by the way, will always be at it's always going to be at the peak of these data points. Because at that peak typically, and we'll call it the mode, at that mode, it's going to split in half there. So we're going to make this little point here. Median will always be near the peak, or we'll call that mode. Okay, so anytime you have peaks, by the way, in the data, those are what we're going to call modes, and hopefully that makes sense. It's the values that occur the most because they're the highest peaks. It's the highest frequencies. Okay, so that's one of the notes. Now let's talk about the mean. Here we have our test data from test 1, and if we graph it, this is the raw scores, which, by the way, here's the comparison between the 2 years. But we would describe our data, if we go back to it, as roughly symmetric, like extremely roughly symmetric. So it's going to look the most like our symmetric data. So where does the mean go in this data? We know the median is at the peak, but for roughly symmetric data or perfect symmetry data, what happens to our mean? Well, we're going to go over here and we're going to run our statistics. We're going to do menu, and if you want to have this open in your calculator, you can do the test scores 2020, go over to the side, and we're going to do the stat calculations for this, and we want to do 2020 raw data. And so we get a mean of 68.23, and then we want to know the median. So let's go to the median, 67. So they're really close to each other. So let's imagine that this is our data. So on this one, we're going to say when it's, and this is typically going to be the rule, when they are symmetric, the mean will be approximately equal to the median. So we're going to put mean here as well. All right. So we're just going to leave it like that, and hopefully that makes sense. Well, I'll write the note. For symmetric data or distributions, the mean is approximately equal and to the median. That's pretty much always, it's gonna always be true. So the reason we're going over this is because our test is coming up, and you will have test questions about this. Okay, I'm going to present a piece of data, and I'm going to say you're going to look at the shape of it, and you have to pick where are the relative positions, where should they be based on if it's symmetric, skewed right, skewed left. So we looked at a skewed right distribution. We talked yesterday about how like somebody like Jeff Bezos would skew up that data really bad. He would be an outlier, and it would cause trouble for the mean. So let's kind of replicate that and see that happen in our data here. Let's watch the mean here. So 68 is the mean. But what happens if I make this data more skewed to the right? How would I do that? Well, that means I need to add more outliers on the right side, which means I need bigger values. So this is what I want to do. I want to pick a value in here, and I want to move, let's say even over here. Actually, let's just do one over here and just make it bigger. So let's go to our test one raw data, and the mean was 68. So let's take the 72 on row 5, and let's change that to a 100. Okay, let's say they got 100 on the test. So let's go back over here, and you can see it changed a little bit, but not a whole lot. Like let me go ahead and write this down. So you don't have to write this, it's just me keeping track of it. It's 68 point, let's go back to it. 68.9487. So this is the, I'm going to call that 2 because that's our second mean from our we moved that point. Okay, did the median change at all? Let's go down there. Median was 67, so it stayed the same. Okay. Now, to really see this, we need to go super extreme, like to values that don't exist. For instance, you can't get over 100 unless you have bonus. But let's pretend like somebody got a 200 on the test. Okay? And let's see how that affects things. Now you can see the average has now changed to 71. What happened to the median? The median stayed the same. Okay, so what we're seeing here is that making this outlier, let me go to our data here. Hold on, I think I just got to regraph it. There we go, look at that. So we have this, that outlier is pulling, so the median is still here at 67, this mode, okay? But the mean is starting to shift to the right, okay? So it's at 71. So I'm gonna write that down. So the 71, so the third mean that we've calculated is approximately 71. Let's get really ridiculous with it. Let's put in a test score of 2000. Impossible, right? But it's really going to show this point of how outliers affect data. Look at that average. That is impossible. You can't have 117 average test score based on our data. What about the median? Did it change? It did not change. So we're starting to see the impact of these outliers even more. I think it's something we've discussed, so let's regraph this. Fix our scale here. Look at that. So the scale has all this data stacked up, and 117 is like right here-ish, but there is no test score that actually holds that value. But this outlier is really causing trouble for this. 117.6. So we'll say the fourth one is 117.6. Okay, so we're seeing that for these distributions skewed right, it's dragging the mean to the right. And that's what you're going to say for relative position. The mean be greater than the median in skewed distributions. Okay? So I said don't write this down here. You are going to write what I just wrote. Mean greater than median in skewed right distributions. And we're going to write this. For skewed right distributions, mean, what did I just write? The mean is greater than the median. And I'm going to say to the right. It takes on a higher value. Again, that's just like the money idea. Why we don't use average for money, we use median, because it is more representative of the true center of the data, that midway point, 50% to the left, 50% to the right. So the opposite will happen on skewed left distributions. So let me go back here. Let's change this back to its original value. I think it was a 72. And then let's go back to our distribution. Let's fix this. Okay, so here it is, back to the symmetry. But now we want to mess up this left side, okay? We want to take one of these left lower values and we want to make it an outlier. So let's see if we can find one, okay? Let's go with 56 here. Let's make that a 0. Anytime you have a 0 in the test score, actually, hold on. Let's see what our mean was to start. It was 68.2308. Okay, so 68.2308. Let's change this 56 to 0. And that takes it down to almost 2 points average right there. If we go down here and we look at it, we see now that this outlier is pulling that data to the left. And did the median change at all? No, it didn't. The median did not change. So we're starting to see on this left side the same effect is happening to the mean. Now, to go any lower, we have to go into the negatives, which isn't possible on a test. A 0 is the lowest score you could get. But let's go ahead and do negative 100 and see what happens. It goes down to 64. Did the median change? No, it's still at 67. So that middle point is still there at that peak. Let's see what this looks like. There it is. So we're past that y-axis there of 0. We're on the left side. Okay. Let's get in a very extreme value in here. Where did I put that? Here it is. Negative 1,000. Let's go over here. Let's check it out. 41 is the test average now. 41. It cut it in half when we did this. And again, we're seeing that formation like we just saw. The scale is causing these dots to stack up. But that outlier is shifting that mean down to the left. Okay, it's going this way. The median is still where it always has been. Like, we can confirm that. Let me go back. We can go down and confirm that the median is still 67. It has not changed. So we are seeing that it's pulling the mean this way as we have outliers. So we would say the mean is down this way. So this would be the mean. Okay? And for skewed left distributions, the mean is going to be less than the median. So write that in your notes. Mean is less than median. All right. So we have one more little note for this, and then we got one more section, and then we'll be done with this unit. So for skewed left distributions, the mean is less than the median. And it goes to the left. All right, cool. So we've got that down now. That is going to be extremely important. It's a test item for our test that's coming up. So you need to make sure you remember that. Now, the last thing we want to talk about is what's called resistant statistics. Resistant statistics. So we're going to write down a definition right here. A statistic is, and when we say statistic, we're talking about the summary statistics. So we're talking about all of these here, right? All of these are statistics. A statistic is, quote, resistant if they are relatively unaffected by unusual or extreme values. So we're going to use the same example that we used for up here, because we see that one of these statistics, mean or median, is going to be resistant and one of them is not. Okay, but we're going to talk about all the statistics. Okay, so we're going to make a list. We're going to have resistant versus not resistant. And we're going to start with the mean. Is the mean resistant or non-resistant? So you're going to answer that for me. Is it affected by outliers? And you should have put yes on this. So we saw that as soon as I was changing the numbers in the data set, as soon as I changed this was 56, so we go back over here, that puts it back to 68. However, the median never changed right here. I go back to that 56 and put negative 1,000, and it auto calculates back to the 41. So it's changing because of those outliers when the median is not. That's the idea of resistance versus not resistance. So we would say that the median is resistant, however, the mean is not resistant. So now we want to talk about standard deviation. So let's go up here. Standard deviation, when it's negative 1,000, the standard deviation is 171. That seems extremely large. Let's go back to 56. 12. So there's a huge difference in standard deviation, which makes sense because it's the average distance from the mean. So if this negative 1,000 is put in, this is a very far point, even from that mean that mean of 41. It's very far from that, hundreds of values away. Negative 1,000. Going over here, standard deviation, 171. It's a humongous change. Okay, so we are going to say that standard deviation is not resistant. So we're going to put that in this column, standard deviation. So let's talk about some of our other statistics on here. So we've got mean, standard deviation, and median. What about minimum? Which you can see the minimum is now negative 1,000. So that was changed pretty drastically when I put that in there. Maximum didn't really change until I did the other direction. But you'll notice these, what about the quartiles? The quartiles, they haven't really changed. Let's go back over here. So if I go from 1,000 back to 56, let's go to quartile 1 and quartile 3. 56 and 78 go back to 1,000. Negative 1,000. We go back over here and we have 56 and 78. So these are not changing. So over here, resistant is going to be Q1 and Q3 are not going to change. What do we calculate with Q1 and Q3? Well, that would be the IQR. Which IQR is used for measuring spread. So I'll put that in front of spread. Not center, but spread. So that's why we use IQR for distributions that are skewed or have big outliers, is because those Q3 and Q1 don't change. Okay. And we saw that standard deviation, it did change. So we put that over here. So for these distributions that are skewed, we use IQR to describe spread, but symmetric, we use standard deviation. Okay. So let's talk about maximums and minimums. With the maximums and minimums, which I kind of said we're not using this anymore, but we can calculate range. So range is directly affected by your outliers because that's the maximum and the minimum. And that's why we said range is not as useful anymore, because it is affected by outliers. And it would be better to use standard deviation for symmetric data anyway. It gives us a better idea about how the average distance from the mean is more important than the greatest minus the least. Okay, the actual range. Okay, so these are all the statistics that are either resistant or not resistant. So this is an important idea for data understanding. And when you're comparing two data sets, it's good to compare the median and the mean first to see if there's any skewness, and then you can make the appropriate judgments on what you should use for spread. So I would compare median to mean, and then go from there. So that's going to be it for this video. It went 22 minutes long, but I'm going to go ahead and stop it, and this will be the last one that we have. You will have a practice quiz that's coming out probably next week that you'll be doing before you take your actual quiz. So I'm going to go ahead and stop here.